glad you're going to see that with Elena. By yourself. Although you wouldn't have minded. What I want you to do, I want you to tell me when you get back how many guys were there. 2 tickets? Oh, that's crazy. Wow, I think you're right. Yeah, there's only 2 tickets. That's pretty good to have a private screening for that cheap. Test, test.
Good evening and welcome to day one of the CSET workshop. Can you guys hear me? There should be a chat box for you guys to type in. So yes, you guys can hear me. If it's not clear, let me know. I can try to adjust the settings over here. Let me turn on for a second my camera so once that you guys can see how I look like. I will normally always turn the camera off so that we have a little bit more bandwidth to play with. So here's how these workshops typically are going to go. I email you guys the material. We go over that material. We work out any exercises or examples that I have. Then after the lecture, I will probably tomorrow email you guys a bunch of exercises. That's for you guys to work on. That's about the material we just saw. And then by the next lecture, I will email you guys the solutions to those problems. Okay, so that's roughly it. Every lecture will be recorded. As of right now, we're not started yet, but I will make sure to record every lecture. And in order to view the recording, you just got to click on the same link that you use here to tonight, participate in the lecture. It's exactly the same link. It will lead you to the recording, and you can download that recording as well, which I definitely would recommend. Okay, so with that said, let me turn off the camera, record the session, and let's get started. Okay, so tonight will be all about trigonometry. So in trigonometry, we talk about angles, of course, and there are two very standard ways for us to measure angles, namely using degrees and radians. Whenever we're working in calculus, and with that I mean whenever you are graphing or deriving or integrating, you have to work in radians. So it's a typical calculus thing that we have to work in radians. The reason is you might remember, for example, that the derivative of sine x is cosine x. That is only true if x is in radians. If x is in degrees, the derivative of sine x is not cosine x. So in calculus, we need to work in radians. But in real life, or practically, we work in degrees. I think in degrees as well when I think of an angle. So what is the relation between degrees and radians? Is what is a full rotation going around the circle once? That is 360 degrees. In calculus, it is 2 pi radians. So if we divide both sides by 2, we get the main formula that relates degrees and radians is 180 degrees is pi radians. Mostly we don't even write down the word radians anymore, and we don't write anything down. So if you don't have any units involved, that means you're working in radians. So if you write down 60, that means 60 radians. If you want it to be degrees, you really have to write down that little notation here for degrees. You should be able to convert between degrees and radians. So how can we do this? Well, we use this formula here that we have to change degrees into radians and radians into degrees. What is the easiest, and this is true for any kind of conversion, it's always easier if you want to go from one unit to another if the unit you start from is a 1. So if I want to go from degrees to radians, if I want to know what x degrees is in radians, I'm trying to change this 180 into an x. So how can I do this? Only using multiplying and dividing. I first divide by 180, then this becomes 1, and then I multiply by x. So x degrees, what is that in radians? You multiply by pi over 180 degrees. The degrees cancel out, and you are left with just a number. You are there in radians. Similarly, how could you go from radians to degrees? You first turn this pi into a 1 by dividing by pi, and then multiply by x. So we get x times 180 degrees over pi. And so that's how we convert from degrees to radians or radians to degrees. Some angles are what we call standard angles. And so let's list them both in degrees and in radians. What are the standard angles, I would say, in degrees? 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. But you also need to know what they are in radians. So let's start with 30 degrees. What is 30 degrees in radians? So we have, again, 180 degrees is pi radians. So to turn that into 30, I can just divide by 6. It's pi over 6 radians. 45 degrees. We divide by 4, so we get pi over 4. 60 degrees. We divide by 3. 90 degrees. We would divide by 2. So if they are nicely going into 180, it's easy. And then finally, 0 degrees is just 0 radians. Okay? So those are some of the standard angles, and they will definitely keep showing up tonight when we talk about the trig functions. There are 6 trigonometric functions. What is a trigonometric function? It's a function whose input is an angle, which of course in calculus must be in radians, and the output is a number. I think it's very important that you see those trig functions like that. They send an angle to a number, because then what will the inverse do? It will send a number back to an angle. Okay? So trig functions send angles to numbers. There are 2 very basic ones, the cosine and the sine. So the cosine of theta, for once in math, the names of the functions have 3 letters. So the name of the function here is cos, cosine of theta. And then we have also the sine of theta, denoted sin. Those are the 2 basic ones. If you know those 2, you can rewrite all the others in terms of cosine and sine. Namely, we have the tangent of theta, and the tangent is defined as sine over cosine. And then we have 3 reciprocals. For us, they are not really that important, but I just want you guys to have seen them, just in case they ever show up. So the secant of theta, the secant is the reciprocal of the cosine. The cosecant is the reciprocal of the sine. And the cotangent is the reciprocal of the tangent. So there's several ways to define the cotangent. It's the cosine over the sine, which makes it the reciprocal of the tangent. But so the first 2 are the most important ones. These are the basic ones. The basic / main trig functions, sine and cosine. To be more accurate, we should really use parentheses here because it's a function. However, If there is no way to misinterpret it, we don't write the parentheses down. So if it's only one symbol, most people will not write any parentheses. If you want to emphasize it's a function, you can. Okay, so that doesn't help you, of course, to know what they are. It's just the name of them. So now we're going to define what these functions are. There are two very important ways to see the trig functions. The first one is in a right triangle. However, by limitations of a right triangle, this will only work for acute angles. So when you work in a right triangle, you're dealing with angles that are strictly between 0 and 90 degrees or between 0 and pi over 2 radians. I always say your best friend in trigonometry is the unit circle. On the unit circle, we can talk about any angle. Positive angles, negative angles, angles that are bigger than 90 degrees, smaller than 90 degrees, it doesn't matter. The unit circle is a generalization of the right triangle. So let's get started with the right triangle. So in a right triangle, what is the setup here? We have a right triangle and your acute angle theta. Then we can give the names of the sides of a triangle, or we can name them. This side is always called the hypotenuse. The other two sides are normally called legs. And in general, you cannot distinguish between them. However, we can call the leg that is used in the angle theta the adjacent leg, and the leg that is not used in the angle is called the opposite leg. And then we can define what the sine of theta and the cosine of theta are in a right triangle. What is the sine of theta in a right triangle? Opposite over hypotenuse. And the cosine of theta is the adjacent over hypotenuse. Since these are the main two, that means you can write down all the others by just using the definitions. So the one that's still, I think, important to see is the tangent. What is the tangent? That was the sine over the cosine. Let me use abbreviations. The sine was opposite over hypotenuse. The cosine was adjacent over hypotenuse. When we simplify these fractions, that's just opposite over adjacent. So the tangent in a right triangle is opposite over adjacent. Okay, so there we have our three definitions of the trig functions in a right triangle. You might wonder if this is really well defined, because I didn't specify which right triangle you have to draw. Just any right triangle as long as this is angle theta. It turns out we did that, I think, in the CSET 2 workshop. If you would write down two of these triangles, they would be similar. And similar triangles give you equal ratios or constant ratios, and that's how you can prove that this is well defined. So it does not depend on the triangle you draw. Okay, so if I go back to the presentation, here's a summary of what we just talked about. Right triangle, the sloped side is always called the hypotenuse. The leg used in theta is the adjacent leg. The side not used is the opposite side. Then the sine is opposite over hypotenuse. the cosine is adjacent over hypotenuse, and the tangent is opposite over adjacent. I know there are some tricks on Memo to memorize them, Sokotoya or something like that. That's fine. I did not grow up in the States, so I never learned it through Sokotoya. I had to learn them with this here. Okay, so that's in a right triangle. How does that work now for the unit circle? Oh, sorry. Before we get there, purely based on this definition, we can now come up with a table for the major angles. Namely, here is that table. So the angles I wrote down are 0, pi over 6, pi over 4, pi over 3, and pi over 2. Or in degrees, 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. I typically write down, if I ever have to write this down, the sine first, and then the cosine, because then the tangent I can get by just taking the quotient. So the sine is 0, 1/2, root 2 over 2, root 3 over 2, and 1. And the cosine is just the opposite. And the tangent, you take the quotient. There is a little, it's actually pretty neat to write them down a little quicker, is that they all actually satisfy the same pattern, namely they are a square root over 2. 1/2 can be thought of as square root of 1 over 2. 0 is square root 0 over 2. And lo and behold, 1 is square root 4 over 2. So the entries in the table look kind of nice. It's square root 0 over 2, square root 1 over 2, square root 2 over 2, square root 3 over 2, and square root 4 over 2. Are these angles mathematically this important? No. However, they are just about the only angles for which we know those trig functions exactly. So why do those angles all of a sudden become so important in calculus? It's really, we can ask questions on an exam that you're not allowed to use a calculator, then it must always be about these angles. Otherwise, you cannot evaluate anything. Last remark, where do these values come from? We did that in the CSET too. Let me maybe quickly show that again for 45 degrees. So for 45 degrees, what would I need to do? I need to draw a right triangle, and one of the angles need to be 45 degrees. I can choose one side to be whatever I want to be. I could draw a triangle like this and make this side 1. But that's it. Now I have to try to figure out all the others. Well, if we start like that, then what can you tell me about this angle? It must also be 45 degrees. So that makes it an isosceles triangle. But then what is the other leg? Also 1. So then we can figure out the hypotenuse. How much is the hypotenuse? 1 squared plus 1 squared, which is the square root of 2. Okay, so I figured out in the table, the question was, do I prefer square root 2 over 2 versus 1 over root 2? Absolutely not. In most standard cases, people like to write their answer without a square root in the denominator. Rationalize your answer, because then everybody has the same answer. There was historically a reason for that is that it's also easier to evaluate by hand. But nowadays, it really doesn't make a single difference. And in some cases, writing 1 over root 2 is easier than writing root 2 over 2. So you're absolutely fine to write 1 over root 2. Mathematically, it's perfectly okay. Back to this guy here. Well, now I can see what the sign is. The sign was opposite over adjacent. Opposite is 1. Opposite over hypotenuse. The sign is indeed 1 over root 2. And if you do want to rationalize this, you get root 2 over 2. Same with cosine of 45 degrees. The adjacent side is also 1. And then the tangent, either you take the quotient or you say that it's opposite over adjacent and we get 1. Okay, so that's how we can come up with the values of the trig functions for 45 degrees. And similarly, but a little bit harder, you can do 30 degrees and 60 degrees. Okay, so that's trigonometry in a right triangle. Let's have a look at one of the questions that was released by the CSET that we can already answer with what we've seen right now. So, question number 3. Use the diagram below to answer the question that follows. So, the diagram shows a rectangle inscribed in a circle of radius r. What is the area of the rectangle as a function of the angle theta? Okay, so what is the formula for the area of a rectangle? Length times width. So the area is length times width. And let me maybe use some color. Or base times height. This would be L. And then here would be the width. How is that related to that r and that theta that is given there? Well, here we have a little right triangle. So if I rewrite that triangle once over here, this is the radius, here's the angle theta. I can figure out the other sides in terms of r and theta. What is the relation between these two sides? So what is this guy here, the adjacent side, in terms of L and W? So this guy here is not L, but it is indeed L over 2. It's only half of L. And how much is the opposite side? Half of W. So I want to figure out what W and L are. Well, let's look in this triangle. I have W, R, and theta. Which trig function relates W, R, and theta together? For that, you have to think about what these sides are. R is the hypotenuse. W over 2 is the opposite side. Opposite over hypotenuse is indeed the sine. So the sine of theta is equal to opposite W over 2 over R, which is W over 2R. So solve for W. W is 2R sine theta. Similarly, L over 2 R and theta are related by which trig function? That's the cosine because L over 2 is the adjacent side. Cosine of theta is adjacent over hypotenuse, which is L over 2r. So solve for L. L is 2r cosine theta. So what is the area of this rectangle? 2r sine theta times 2r cosine theta. So that is 4r squared sine theta cosine theta. And although there are plenty of ways to rewrite this, what seems to be the answer? D. They are using an absolute value. It doesn't hurt, but the way they drew theta on the picture, theta is an acute angle, so its cosine and sine would be positive. Okay, so this is just an example of trigonometry in a right triangle. The second method to look at, or the second way to look at angles in trigonometry is on the unit circle. But before we can talk about that, we need to talk about how do you graph an angle on the unit circle. So we agree that we are going to graph our angles in standard position. What is basically an angle? It has two sides and a rotation between them. So it has an initial side and a terminal side, and then it's whatever is between the initial side and the terminal side. So when you graph an angle in standard position, we agree that we're going to put the initial side on the positive x-axis. Then you need to do a rotation to get to your terminal side. If our angle is positive, we are going to rotate counterclockwise. In mathematics, the positive direction is counterclockwise. If theta is negative, we're going to rotate clockwise. When we do that, we will have our terminal side will intersect the unit circle at a point xy. And then we can start reading off the trig function. So let me do that here on the board. So we have our unit circle. Let me see if I can draw that nicely. X and Y. The unit circle means that the radius is 1 and the center is the origin. So we start by graphing an angle. So here's the initial side. Let's say that I made a positive angle. So I go counterclockwise. And here is my terminal side. That terminal side intersects the circle in something that we call a point P. And that point, of course, has an x coordinate and a y coordinate. So make that a little smaller. Where on the axis do you see the x coordinate of a point? So how does that work, an x and a y coordinate? So do you see the x coordinate on the x-axis or the y-axis? The x is on the x-axis. If you would drop this down perpendicular, then here would be your x. And similarly, where do you see the y? That would officially be the y-axis, so that would be here. And then this part would be your y. Which means I don't really need all of that. Where can I see my y now? My y is this. And because I'm working on the unit circle, this distance here is the radius, which is 1. And now we can see that we have a right triangle. Hypotenuse 1, the adjacent leg is x, and the opposite leg is y. So using trigonometry in a right triangle, what is the cosine of theta? The cosine of theta is adjacent, which is x, over hypotenuse 1. So that's just x. The x-coordinate of that point on the unit circle is the cosine of the angle that it came from. Similarly, where's the sine? Well, that's opposite over hypotenuse, which is just y. The y-coordinate is just the sine. Can you actually see in this picture the tangent? The answer is yes, but it's a little harder. So let me write that point here, xy, so I have some more space. Oh, sorry. That was, I don't know what happened. My apologies. I'm going to quickly have to sketch this again. Okay. I must have hit a button and it disappeared. All right, so here's my triangle. If you look at the tangent line to the circle here at that point on the x-axis, so that would be this line here. What is the equation of this line, that tangent line? So it's a vertical line, so it has the equation x is 1. And I would like to figure out what the coordinates are of this point. Well, the x-coordinate is 1, but what is the y-coordinate? Well, look in the, of this point here, the y-coordinate is not 0. It's not so obvious. What is its y-coordinate? Its y-coordinate would be whatever this distance is. Right? Because that's how I would project it down. So if I call this, let me write h. If you now look in the big triangle, I don't know the hypotenuse, but I know the opposite leg is h, and the adjacent leg is 1. So in that triangle, opposite over adjacent is the tangent. Tangent of theta is h over 1, which is h. So the second coordinate of that point is the tangent. That's how I recognize the tangent on the unit circle. After graphing it in standard form, I have to extend it. I extend my terminal side till I hit the tangent line x is 1, and then the second coordinate is the tangent. Right? So let's recap how you recognize all these things on the unit circle. You start with the initial side, terminal side, you have a point on the unit circle. Its x coordinate is the cosine. That's here. Its y coordinate is the sine. That's here. The tangent is y over x, but where do you see that in the triangle or on the unit circle? Extend the terminal side till you hit the line x is 1. Then the second coordinate of that point will be the tangent. That's where you recognize y over x. Y over x is also the slope of this line, but again, that's harder to recognize. Okay, so you're probably very familiar with seeing the sine and the cosine on the unit circle, but you should also learn to see the tangent there. Okay, so some people, they like working. What if you work on a circle, but it's not the unit circle, but a circle with radius r? Well, that would mean that instead of 1, you have r here. Well, then what would be the cosine of theta? X over r. So x would be r times the cosine, y would be r times the sine. I typically don't use those formulas, but I know that they are out there. So x is r cosine theta, y is r sine theta, y over x is still tangent theta. That's only if you do not work on the unit circle. Okay. The unit circle, besides being useful for many other things, is also very useful if you need to evaluate the trig functions when theta is a multiple of pi over 2. Namely, angles, when you graph them on the unit circle, you're at one of the 4 points of intersection between the circle and the coordinate axis. So let's see this in action. Let's try to figure out what the sine, cosine, and tangent is of negative pi. So I start by drawing the unit circle. Next, I need to draw the angle in standard position. The initial side is always the positive x-axis. Am I now going clockwise or counterclockwise for a negative angle? I'm going clockwise, so I gotta do something like this here. How far? Well, forget about the negative, whatever pi is. It's really useful to think in degrees as well. How many degrees is pi radians? 180 degrees. So I am rotating clockwise 180 degrees. Where do I end up? Over here. So this here is the terminal side. So I end up at this point. I can read off what the coordinates are of that point. So here's my angle, negative pi. That's this guy. What are the coordinates of this point? X is negative 1, y is 0. But I know that they have something to do with sine and cosine. Which coordinate is the cosine again? The x. So that's also cosine negative pi, sine of negative pi. So conclusion, the sine of negative pi is What is the sine of negative pi? Is 0, the y coordinate. The cosine is -1. And then the tangent, I just divide sine over cosine. And so we get now 0 over -1, which is 0. But the method to find the tangent would work. What would you do? You would extend the terminal side till you hit the tangent line x is 1. You would end up at this point. That point has coordinates 1, 0, so that should be the tangent. But it's much easier if you know the sine and the cosine to just take the quotient. Okay, so you can't do this with a right triangle. It's 1, it's a negative angle. 2, it's a multiple of 90 degrees. Let's do another one. Let's find the trig functions of 3 pi over 2. So we start with the unit circle. We're going to graph 3 pi over 2 in standard position. Here's the initial side. Am I going clockwise or counterclockwise? Counterclockwise for a positive angle. And somebody told me indeed this is 270 degrees. So where do I end up? Well, 90 degrees, 180 degrees, 270 degrees. So on my terminal side will be this. And I end up over here. What are the coordinates of that point? X is 0, y is -1, and that should be, the first one is sine or cosine. The cosine. And the second one is the sine. Okay, so cosine, or sorry, let me write, sine of 3 pi over 2 is -1. The cosine of 3 pi over 2 is 0. And what is the tangent? I divide sine over cosine. -1 over 0 does not exist. Could we have done this with our tangent line method? Sure. Here's the line, x is 1. What would I do? I would extend my terminal side until it hits the line x is 1. I can extend this all I want. They are parallel. So they never intersect. That's why we don't have a tangent. Okay, so very straightforward to evaluate the trig functions of those angles that are a multiple of pi over 2. You need to end up at one of these 4 points. Roughly speaking, because those are the only 4 points that we can find the coordinates of. So how about all those other angles? 30 degrees, 60 degrees, 45 degrees. For that, we will also use the unit circle, but I will need to introduce another concept of the reference angle to explain 2 methods to do that. Using the unit circle, we can now easily see the sine, S-I-N-G-N, of the basic trig functions, cosine and sine. So whether cosine and sine are positive or negative. For example, if you are in the second quadrant, is the cosine positive or negative then? The cosine is the x-coordinate, so the cosine is negative. The sine is the y-coordinate, So the y coordinate in the second quadrant is positive. Again, there's that a little sentence, what is it, all students take calculus or something. It never made any sense to me. You just graph the unit circle and you check where the x coordinates and the y coordinates are positive or negative. To evaluate trig functions at other angles that are not in the first quadrant, there's roughly two methods. The method I prefer the most because it requires the least kind of pure memorization or so is transformations. What you do is you try to get back into the first quadrant. So what are the transformations that you can use? You can reflect about the x-axis, the y-axis, or the origin, depending on which quadrant you are. So I will show you guys that method, but you could also use excuse me, a method called the reference angle. And the reference angle is definitely important. We'll see it in other applications tonight as well. So what is the reference angle of an angle? It is the angle, an acute angle, so it's always between 0 and 90 degrees. There is no such a thing as clockwise or counterclockwise. No, it's an acute angle, and it is formed by the terminal side and the whole x-axis. So the terminal side will always make two angles with the x-axis. Just pick the acute one. That's called the reference angle. What property does the reference angle have? For that, we need to graph it really, but it turns out that all your trig functions of an angle are roughly plus or minus the trig function of your reference angle. So which one do you pick? Well, that depends on which quadrant you are. Your theta prime, everything is positive because it's an acute angle. So if you're in a quadrant where your sine is negative but your cosine is positive, then the sine of theta would be negative sine theta prime, and the cosine of theta would be positive cosine theta prime. Right? So maybe a little picture to see that reference angle. So let's say that here's the x-axis and that your terminal side is here. Then where would your angle be? The angle would be here. What is the reference angle? Well, there's two angles my theta looks obtuse, so the reference angle would be this guy. Okay. I'm not drawing an arrow on my reference angle. It would be 180 minus theta. If theta is 120 degrees, then theta prime would be 60 degrees. So that is the how you find the reference angle. Okay? So let's have a look. Let's do 3 exercises on finding trig values, sine and cosine and tangent of known angles related to those angles of 30 degrees, 45 degrees, and 60 degrees. And if for each exercise, I will use both methods, the transformation method and the reference angle method. So theta is negative pi over 2. In both methods, you have to start by graphing the angle, at least a quadrant. So here's the initial side. Are we going clockwise or counterclockwise? Clockwise. What is this in degrees? Negative pi over 4 is correct, but it's really, I'm looking at negative 45 degrees. But it would be the same spot as 315 degrees. But when I graph it, I will end up here. So this angle is negative pi over 4. So what are the coordinates of this point? I know they must be the cosine and the sine. I just don't know yet what they are. Okay. Next, I use a transformation to get into the first quadrant. Is it a reflection about x-axis, y-axis, or origin that will get me into the first quadrant? The x-axis. Okay, so then I get this. Now, based on what we've been doing, if this guy is negative pi over 4, then what does this angle need to be? That one is the counterclockwise one, must be pi over 4. So I know what the coordinates of this point are. They're cosine pi over 4, sine pi over 4, and they are known. What is the cosine of pi over 4? Root 2 over 2, and the same for the sine. Now go back to the original point by reflecting again over the x-axis. You end up over here. So if this is root 2 over 2, root 2 over 2, and we reflected about the x-axis, what do these two numbers need to be? The x-coordinate stays the same, but the y-coordinate changes sign. So let's recap quickly. We draw it. We know the coordinates are cosine sine of the angle I'm looking for. In this case, reflect about the x-axis. You get always an angle in the first quadrant. Figure out what this angle is. It's pi over 4. The coordinates of this point are cosine and sine of pi over 4, which we know. Then we reflect back and we're able to figure out these two. So the sine of negative pi over 4 is the y-coordinate negative root 2 over 2. The cosine of negative pi over 4 is negative root 2 over 2. Sorry, it's positive root 2 over 2. And then we can figure out the tangent by taking the quotient of sine over cosine. And that turns out to be negative 1. That's how I figure out these guys, always by using a transformation to get into the first quadrant. Okay, the other method was the reference angle. So let's also answer this question using a reference angle. You start exactly the same way. You still got to graph it. So here's the initial side. Here was the terminal side. And this angle is my theta. So what is my reference angle then? Well, I have the x-axis and I have my initial side. So what is the reference angle? This unmarked, so make it positive. So if my angle is negative pi over 4, then what is the reference angle? Hmm. Um, Not correct, Catherine, but the reference angle is this guy here. Let me mark it again. It's got to be an acute angle. You can answer me in degrees, but it's got to be between 0 and 90 degrees. So how much is this angle? It cannot be negative. So positive, it's 45 degrees. It's pi over 4. That's the reference angle. The acute angle formed by the x-axis and the terminal side. So that is, of course, exactly the same angle that we came up with over here. That will always be the case. Okay? So back to here. What does this method do? Well, it says that the sine of my angle, so sine of pi over 4, is plus or minus the sine of the reference angle. So plus or minus the sine of pi over 4, and the sine of pi over 4 is root 2 over 2. So the sine of negative pi over 4, sorry, there was a typo here, is either plus or minus root 2 over 2. How can I figure out which one it is? Well, here's where we are. At this point in the fourth quadrant, is the sign positive or negative? Negative. So we need to pick the negative. And that's because, yeah, y is less than 0 in the fourth quadrant. And you do a similar thing for the cosine. The cosine of negative pi over 4 will be plus or minus the cosine of pi over 4, the reference angle. That is also root 2 over 2. And now I need to figure out if it's the plus or the minus. In the fourth quadrant, the x is positive. Okay, for everybody? So you don't need to know both methods. You need to know one of them so that you are able to figure out these values. So the reference angle is a way to make everything positive, acute and positive. All right, let's do another one. 7 pi over 6. Let's maybe immediately write that in degrees. What is 7 pi over 6 in degrees? 210 degrees. So I started in standard position, clockwise or counterclockwise? Counterclockwise, positive angle. So in which quadrant do I end up? Third quadrant, 90 degrees, 180 degrees, a little bit more, 210 degrees. Okay? So this is 7 pi over 6. My terminal side is here. I intersect somewhere here. So the coordinates of that point, I know, will be cosine of 7 pi over 6 and sine of 7 pi over 6. I just don't know what they are yet. So we use a reflection to get into the first quadrant. Which reflection do I use to get into the first quadrant? X-axis, y-axis, or origin? I need to reflect across the origin. Across the x-axis, I would end up here. The y-axis, I end up over here. But I do the origin, which gets me over here. Reflect about the origin. Then, using some geometry or whatever, if this whole thing is 210 degrees, we should be able to figure out what this is. How much is that angle? Indeed, Vanessa, it is pi over 6, 30 degrees. Because that half circle is, of course, 180 degrees. So, the coordinates of this point must be cosine pi over 6, sine pi over 6. And those two are known. What is the cosine of pi over 6? Yes, Andrew, but that is the next method. So then I will show that also with the reference angle. So here I'm doing the method now with the reflecting. That means I gotta get into the first quadrant, figure out what that point is, and then go back. So what is the cosine of pi over 6? Root 3 over 2. And the sine of pi over 6? Is a half. Now go back one more time. If you know that this is root 3 over 2 and 1/2, and I reflect about the origin, what does this need to be? What happened to your x-coordinate when you reflect about the origin? It changes sign, so the x-coordinate becomes negative. And how about my y-coordinate? Similarly, it is negative. Okay, so graph it, get into the first quadrant, figure out the coordinates of that point, then figure out the coordinates of the original point. So we now know what the cosine and the sine are. The sine of 7 pi over 6 is negative a half. The cosine of 7 pi over 6 is negative root 3 over 2. Take the quotient, and the tangent of 7 pi over 6 is negative a half over negative root 3 over 2. That becomes 1 over root 3, or root 3 over 3, if you want to rationalize. What I really like about this method is that you will not miss a negative sign. You can just see it. Know the x-coordinate has to be negative, y-coordinate has to be negative. Okay, how would that work with the reference angle? Well, you first would have to find the reference angle, so we still end up graphing it. We know where we end up, third quadrant. So this whole thing, let me work in degrees here, is 210 degrees. What is the reference angle? X-axis and the terminal side. It must be the acute angle, so the reference angle is this guy here. How much is this angle? $30 using 210 degrees minus 180 degrees, 30 degrees, or indeed pi over 6. So then what would we have? Let me work for ones in degrees. The sine of 210 degrees is plus or minus the sine of 30 degrees. The sine of 30 degrees is a half. So we need to figure out at 210 degrees, we are in the third quadrant. Is the sine positive or negative? It's negative. And similarly for the cosine. Plus or minus the cosine of the reference angle. Cosine of 30 degrees is root 2 over 3 over 2. In the third quadrant, is the cosine positive or negative? Negative. So there was a question, are we allowed to use degrees on the CSET? Yes. When you're evaluating something, of course you can write degrees. However, your final answer might have to be, of course, in radians. But I have a feeling, for me personally, it's much easier to think in degrees than radians. But if you are used to seeing or saying that this is pi over 6, by all means, keep it like that. I think of it as, that's 30 degrees. So that seemed to be easier. Somebody wrote negative 30 degrees. Reference angle is always positive. That's the whole point about the reference angle, is to make it all positive. And then you have to deal with the plus or the minus at the end. Okay, one more. 2 pi over 3. What would that be in degrees? 120 degrees. 2 times pi over 3, 2 times 60 degrees, 120 degrees. So we start by graphing it in standard position. Clockwise or counterclockwise? Counterclockwise, we have a positive angle. So in which quadrant do we end up? Second quadrant. We end up somewhere here. So that would be 2 pi over 3, which means the coordinates of this point, I know, will be cosine 2 pi over 3, sine 2 pi over 3. With the reflection method, which reflection do we use to get into the first quadrant? Over the y-axis. So reflect about the y-axis. We get over here. So I need to figure out what this angle is. This one is the hardest one, but it is pi over 3 or 60 degrees. Why? Well, this was 120 degrees. So that means this guy is 60 degrees. And that's the one we reflected over. So that would be 60 degrees. So the coordinates of this point are cosine pi over 3, sine pi over 3, but that is a known angle. The cosine of 60 degrees is a half. The sine is root 3 over 2. So now perform that one more time. Go back to the red point. If we know that point in the first quadrant, and we reflect back over the x-axis, then this point must be what happens to the x-coordinate, what happens to the y. The x-coordinate becomes negative. The y-coordinate stays the same. So we get the sine of 2 pi over 3 is root 3 over 2. The cosine of 2 pi over 3 is negative a half. The tangent of 2 pi over 3, take the quotient of sine and cosine, and we get negative root 3. That's the reflection method. Let's also do the reference angle method. So again, we graph it, standard position. Where's the reference angle? The reference angle is the acute one, so this here should be the reference angle. That's the reference angle, which is easier even than the one we had with the reflection method. 120 degrees, whatever is left over 60 degrees, so pi over 3. Then we use that. What is the sine of 2 pi over 3? Plus or minus the sine of the reference angle. Sine of pi over 3 is root 3 over 2. So we need to figure out if it's positive or negative. Is the sine in the second quadrant positive or negative? The sine is positive in the second quadrant. Y is positive. But for the cosine, we get plus or minus the cosine of the reference angle, plus or minus a half. That one is indeed negative. In the second quadrant, the x-coordinate is negative. So in either method, you have to graph it, and you have to basically come up with the reference angle. Okay, so this method can also be used to evaluate, and this is a very standard question, is you are given one trig function, one value of a trig function, and you're asked to find another one. That by itself is not good enough. So not only do you need to know one trig value, you also need to know in which quadrant your angle is, or something else must be given. So here we know that the tangent of theta is negative 3, and it is given that the sine of theta is negative. So we need to figure out in which quadrant we are. I tend to not work too much with those trig identities that we will see later on, but just graph a little right triangle. Some people draw it right on the unit circle. You got to be careful with that. The side of a triangle should actually never be negative. So let's figure out the tangent of theta is negative, and the sine of theta is negative. This indeed means that the cosine must be positive, because the tangent is the sine over the cosine. So, in which quadrant are we that the x-coordinate is positive, but the y-coordinate is negative? That is indeed fourth quadrant. Theta is in quadrant 4. Okay. I tend to now work with a right triangle with the reference angle. Use a right triangle for the reference angle theta prime. So how does that work? Well, I have myself a right triangle and theta prime is here. What do we know? The tangent of theta is -3. So what is the tangent of the reference angle then? Remember, it's an acute angle. Everything has to be positive. So the tangent of theta prime must be 3. What is the tangent in a right triangle? That was opposite over adjacent. So can you come up with two numbers? I'm going to write this in blue. So you need to come up with this side and this side, but the quotient should be 3. We pick the easiest one is 3 and 1. Or 1 and 3, so 3 and 1. Opposite is 3, adjacent is 1. You could also pick 6 and 2, but easiest is 3 and 1. Then you can use Pythagoras to figure out what the hypotenuse is. How much is the Pythagoras? The hypotenuse is indeed 1 squared plus 3 squared squared, which is square root of 10. But now I can figure out anything about theta prime, and hence also about theta, by just looking at that triangle. We already knew the tangent of theta was -3. So let's look at the sine, and then we'll do the cosine as well. The sine of theta is plus or minus the sine of the reference angle. The sine of the reference angle is opposite over hypotenuse. So now the only question is, should we pick the positive or the negative? Well, it was given that the sine is negative, or we quickly look in the fourth quadrant. In the fourth quadrant, yeah, our sine should be negative. What else are we missing? The cosine. The cosine of theta is plus or minus the cosine of theta prime. What is the cosine of the reference angle? Root 10 over 10 or 1 over root 10. Adjacent over hypotenuse. And we should be positive because in the fourth quadrant, the cosine is positive. So I really make a point of it not to write theta here, but theta prime. This is a right triangle for the reference angle. I know that some people do something like this. I'm going to attempt it and then quickly probably stop it. So they draw it on not the unit circle, but a circle. We're in the fourth quadrant. So our angle is somewhere here. And then they have to come up with an X, a Y, and an R. Then you have to remember that the tangent is y over x and that your y needs to be positive or negative in this case. So then people look at this right triangle here, but it's not really the triangle that they're filling in. They are filling in the numbers x, y. So then they would make y negative 3 and x equal to 1. R is always positive. R would be square root of 10. I do not like that method so much, but if that's what you've been doing, you're more than welcome to keep using that. I prefer the method with the right triangle. Everything is always positive in the right triangle with the reference angle, and then we just deal with the plus or the minus at the end. Okay, so that's it for basically evaluating the trig functions. The rest of the evening and a part of the next week's workshop is talking about identities. There are a gazillion identities in trigonometry, and there's a couple that you will need to know for the CSET. We will do more than what you need to know, and I will definitely let you know which ones are important and which ones you don't really need to remember. I just want to show you what you can do. The most famous trigonometric identity is that sine squared plus cosine squared theta is 1, or cosine squared theta plus sine squared theta is 1. Then you can deduce from that one two more identities. 1 plus tangent squared theta is secant squared theta, and 1 plus cotangent squared theta is cosecant squared theta. So let's have a look at the first one. Where does it come from that sine squared theta plus cosine squared theta is 1? Why is that true? If I, roughly speaking, but the unit circle, so how did this work? We graphed an angle theta on the unit circle. So let me just say that this is my theta. Then what are the coordinates of this point, x and y? Which one is the x again? The cosine. The cosine of theta is the x, and the sine of theta is the y. But what is the equation of the unit circle? X squared plus y squared is 1, which is of course Pythagoras, because if I write this out, this is 1, my y would be here, and my x would be here. So x squared plus y squared is 1. So x squared plus y squared is 1. X is the cosine, so cosine squared theta plus sine squared theta is 1. That is the most basic trigonometric identity. It turns out that it's actually equivalent to the Pythagorean theorem. So how could I show you guys that it's equivalent? Well, that means what if I have a right triangle that is not doesn't have hypotenuse 1? Well, what is Pythagoras in this triangle? So what is the Pythagorean theorem in this triangle here? A squared plus B squared is C squared. Well, that is equivalent. I can divide everything by C squared. That's equivalent to saying that A squared plus B squared over C squared is C squared over C squared. I can split this. That's A squared over C squared plus B squared over C squared. And C squared over C squared is 1. One more step. This is A over C squared plus B over C squared. Now, in this triangle here, what is A over C? That is the cosine of theta. And B over C, opposite over hypotenuse, is the sine. So this is showing that Pythagoras and that basic trig identity are equivalent. If Pythagoras is true, then cosine squared theta plus sine squared theta is 1, and vice versa. Okay, so it's basically how do we go from a right triangle with a hypotenuse that is not 1 to a right triangle with a hypotenuse of 1? Divide by the square of the hypotenuse. So that is this identity here. Where or how else is this used? Sometimes, that's more in Calc 2, it is used to replace sine squared theta by cosine squared theta and vice versa. So I could move cosine squared theta to the right, then you get sine squared theta as 1 minus cosine squared theta, or I could move sine squared theta to the right, and then of course we get cosine squared theta is 1 minus sine squared theta. There are a ton of identities again in trigonometry. So these identities like sine squared theta is 1 minus cosine squared theta, by itself that's pretty useless for us. It's only if we have a specific application where we have a sine squared and I want to replace it by cosine squared that this makes sense. And there is an application like that in Calc 2 when you talk about integrals, but we will not see it. Okay, there were two other identities that I wrote down that you might know, namely 1 plus tangent squared theta is secant squared theta. Where does that come from? Well, we still have that cosine squared theta plus sine squared theta is 1. So how could I get the tangent in there? We got to be careful, Jerome. What is the tangent? Is that sine over cosine or cosine over sine? It's sine over cosine. So how could I get sine over cosine in here? I don't want to divide by sine squared, but we divide by cosine squared. So divide everything by cosine squared theta. Now the one that you do is the other one, the other identity, which I'm going to leave for a little homework. All right, so then we can split this. Cosine squared theta over cosine squared theta plus sine squared theta over cosine squared theta is 1 over cosine squared theta. Cosine squared theta over cosine squared theta is 1. Sine squared theta over cosine squared theta, sine over cosine then squared, that's the tangent. And 1 over the cosine is the secant. So It's really not anything new, it's just a different way of interpreting it. When would that make sense? Whenever you need to have a relation between the tangent and the secant. If you would divide both sides by sine squared theta, then you would get this guy here. 1 plus cotangent squared theta is cosecant squared theta. Okay, so especially the very first one, sine squared theta plus cosine squared theta is 1. You gotta know that one. Maybe I should have rewritten it as cosine squared theta plus sine squared theta is 1. But same identity. Very basic one. Okay? Next, we're going to be talking about the opposite angle identities. These are still important. You don't really need to memorize them because you can very easily see them again on the unit circle. So, what are the opposite angle identities? As the name suggests, we're talking about the trig functions of an opposite angle. So, can we relate the trig functions of negative theta to the trig functions of theta? It turns out that the sine of negative theta is negative sine theta. But the cosine of negative theta is cosine theta. And then what should be true about the tangent of negative theta? Will there be a negative sign in it or not? Will it be negative tangent theta or tangent theta? There should be a negative in it. Why? The tangent is the sine over the cosine. So we get negative sine theta over cosine theta. We get negative tangent theta. So the question is really, how can we come up with these first two? Well, let's use our unit circle. Let's do an example. So I graph my angle theta, and just to make it easy, I graph it in the first quadrant. This could be like 60 degrees. Then where is the opposite of theta? So if theta was 60 degrees, where is negative 60 degrees? The only thing I have to do is go counterclockwise, clockwise now. That would be negative theta. And then we can see if these angles have the same magnitude, that means that these 2 points really come from reflecting about the x-axis. So what are the coordinates of this point? Cosine theta, sine theta. What are the coordinates of the purple one? Cosine of negative theta, sine of negative theta. When we reflect about the x-axis, what happens to the x-coordinates? They stay the same. So the cosine of negative theta is the cosine of theta. What happens to the y-coordinate? That one we have to change, so that will be negative the sine of theta. So yes, if I use them enough, I'll remember them. But if not, I quickly draw the unit circle, and I got the identities back. There's a ton of other identities out there. What about pi minus theta, pi plus theta, pi over 2 minus theta, pi over 2 plus theta? You can figure those out, but there's really no need to memorize them. The next one is very, very important, and you should memorize them. Those are the only ones that you should know, I think. The sum and difference rule. So, as the name suggests, we would like to know what is the trig function sine, cosine, tangent of a sum of two angles and of a difference of two angles. So let me give you guys the formulas and then we'll see how to come up with that. The sine of A plus B is sine A cosine B plus cosine A sine B. The cosine of A plus B is cosine A cosine B minus sine A sine B. And the tangent of A plus B is tangent A plus tangent B over 1 minus tangent A tangent B. As usual, the most of the work will be finding the formulas for the sine and the cosine. Because then we should always be able to just come up with the tangent relatively easy. That's the sum formulas. If you know the sum formulas, you can actually relatively easy find the difference formulas. For the sine, A minus B, that becomes a minus here. For the cosine, there's a plus involved now. And for the tangent, this plus becomes a minus and this minus becomes a plus. So I am going to show you guys how to find the form or prove the formula for the sine of A plus B. You guys on some homework are going to do the cosine of A plus B, and then I will do the tangent of A plus B again and tell you guys how to do the negatives. Okay, so how about the sine of A plus B? How could I come up with a formula for the sine of A plus B? Well, let me first try to explain the picture that I inadvertently showed you guys already. So I want a picture that I can deal with angle A, angle B, and angles A plus B at the same time. Well, to be able to work in a right triangle with angle A, I need to draw a right triangle with angle A. Where's angle A plus B? You would just add angle B over here. How can I deal with angle B? I want a right triangle. That has B in it. So in this picture, I can already talk about angle A, angle B, and angle A plus B is in there, but it's not a right triangle. How can I get a right triangle for angle A plus B? I need to drop the perpendicular here. Okay, so that's the standard picture. Now we start writing down a whole bunch of stuff, giving it names, and then see if we can find a formula for the sine of A plus B. All right, so that's where this picture came from. We want angle A plus B, and then angle B as well. So in order to be able to talk about angle A, I should give the three sides of this triangle a name. So I'll try to use some color. This guy, this whole thing is x1. This thing, x2. And here, x3. Okay, then I can talk already about angle A. To talk about angle B, oh, x3 is good. I need the other sides of that triangle, so I do x4 and x5. Running out of colors here almost. But in order to talk about angle A plus B, I only need the sine of A plus B. So for angle A plus B, I need the hypotenuse, check. But I also need this piece here, the height, the opposite side. That opposite side, I could give that whole thing a name, but part of it is x2. So it kind of suggests that I draw the perpendicular here as well, and that I only look at this piece. And I call that x6. Then we are good to go, except that now all of a sudden I have a third right triangle in there, x6 and x4. So it might be nice to figure out if there is a relation, there should be, on these angles of this right triangle and whatever A and B are. I think it might be easiest to just write out if this guy is angle A, then how much is this angle here? So what will this guy be? 90 minus A. Then how much is this one? So what is this figure here? Sorry. So this is a rectangle, right? I got a right angle, right angle, right angle must also be right. So that little piece left must be A again. 90 minus A. All right. Then we're almost there. Now what is this guy then? Huh? There was this right triangle in the triangle for B. So that's a right angle. One angle is A, so the other one is 90 minus A again. Then finally, what is this angle? That's angle A again. So we actually have two triangles that I can see angle A in. The original one, and there's another one. There's, of course, other arguments using a rotation that you can make. I want to erase my calculations there in between. I don't need them anymore. We've deduced that that angle A is also up there. Okay, so we start by, we want a formula for the sine of A plus B. There's a right triangle for the sine for AB, that's this guy here. The sine is opposite over a hypotenuse. What is the opposite side in this triangle for A plus B? That's this guy, which is x2 plus x6. And what is the hypotenuse? x5. Okay. Now I want to start rewriting stuff. What can you tell me about x2? Well, x2 is inside this triangle here. So x2 is an opposite side of A. If we want to avoid using a tangent, then I can express which trig function of A involves x2 and x3 then. That's the sign. So I need to do that here on the side. This is my first step. But now I need to get rid of x2, so we see that x2 over x3 is the sine of A. So what is x2? x2 is x3 sine A. Okay? So I substitute that in here. That's x3 sine A plus something. I need to do something similar for x6. There's only one triangle that involves x6 right triangle. That's this guy here. So it's also going to be related to the angle A. And here I don't even have a choice. But again, if I don't want to use the tangent, I got to use this guy. So which trig function am I using in this triangle? That is this time the cosine, adjacent and hypotenuse. So x6 over x4 is the cosine of A. So x6 is x4 cosine A. Okay, let me substitute that in there. x4 cosine A. I can now split this. That's x3 over x5 sine A plus x4 over x5 cosine A. Based on the picture, what is x3 over x5? That is in this triangle. x3 is which side? That is the adjacent side of B. x5 is the hypotenuse. Adjacent over hypotenuse is indeed a cosine. So this is cosine B sine A plus, and what is x4 over x5? The sine of which angle? So x4, x5 is in the same triangle. x4 is opposite, x5 is the hypotenuse. Opposite over hypotenuse is indeed the sine. So we get sine B cosine A. Huh, that's exactly the formula that we listed, but I wrote it as sine A cosine B plus cosine A sine B. So the proof of that identity is really 3 steps. Right? This was step 1, replacing to get step 2, and then splitting step 3. It's a proof I really like. You might say, does this really work for all angles? No, but it's very easy to explain, and you can see the right triangles in there. Okay, so you guys on the homework are going to do the cosine. For the cosine, you're going to have to split this guy. So you can't call that x1, maybe this piece x1 and that x2, and then you keep going like this. Give everything a name that you need to, and it should be. So we try to come up with this angle by roughly, I should maybe draw this a little bit better. Let me attempt to do this a little bit better, where it came from. So what we're doing here is at this point, I'm dropping the perpendicular. And so that was then my x6. Okay, so here, by looking at the triangle at the bottom, Angle A, 90, so this guy's got to be 90 minus A. Then this whole thing is a right angle. Let me try to write that here. This is also a right angle. So this guy's got to be A again. Then because this is a right angle, this guy has to be 90 minus A. And then finally, that one is A again. So we're always looking at angles that add up to 90 degrees. Okay, so that is the formula for the sine of A plus B. The cosine of A plus B, like I said, I'm going to leave that as homework. So try to do exactly that same picture, but you're going to probably give some different names to these sides. So how could we now come up with the tangent? You might say maybe use the same triangle again. Could be. But do you see an easier way to come up with a tangent if you know the sine and the cosine? The definition of the tangent is the sine over the cosine. So let's see if that would work. So, oh, sorry, I did another one first. Let me quickly check. Yeah, well, let's first do the tangent then. So, what is the definition, or what is the sine tangent of AB? It's the sine of A plus B over the cosine of A plus B. Using our two formulas, we get sine A cosine B plus cosine A sine B. And the formula for cosine was cosine A cosine B minus sine A sine B. And that is a correct formula, but that doesn't involve any tangents whatsoever. So how can I, for example, in the numerator, get the tangent of A in here? Well, I got sine A, so if I divide by cosine B, I'm going to get the tangent. Of course, I'm not allowed to just divide by cosine B. Cosine A, I'm going to have to divide top and bottom by cosine B, A. And similarly, to get the tangent of B in there, I divide by cosine B. So let me take that one extra step. I am going to divide top and bottom by cosine A cosine B. This is something that we do often in math. I'm not changing the value because practically I'm dividing by 1. But I will change the way it looks. Then, of course, we can split. So we would get sine A cosine B over cosine A cosine B plus cosine A sine B over cosine A cosine B. And similarly for the denominator, cosine A cosine B over cosine A cosine B minus sine A sine B over cosine A cosine B. And if we now simplify, we should get there. So here, cosine B cancels out. We're left with sine A over cosine A, which is exactly tangent A. Second piece, cosine A cancels out. We're left with sine B over cosine B, that's tangent B. Cosine A cosine B over cosine A cosine B, that's just 1. And then finally, the last one, we take sine A over cosine A together, sine B over cosine B together, and you get tangent A, tangent B. Okay, so there's no more really trig involved. It's pure algebra at that point. But that's a pretty standard trick. For the tangent, just do whatever you have for the sine and the cosine and divide them. So that gives us the three sum formulas. So how could we now get the formulas for the difference? Do I really have to start all over again? For the sign of A minus B. So do a picture where you have A subtract B. That seems like a mess. It will work, but the easiest way is to view the sum, the difference as a sum. So the sign of A minus B is really a sum formula. That is the sign of A plus the opposite of B. So we can now use our sum formula that says it's the sine of the first, cosine of the second, plus cosine of the first, sine of the second. And now we use indeed the opposite angle identities. What was the cosine of the opposite angle? The same as the cosine of the angle. But the sine of the opposite angle, then there was a negative involved. So we get sine A cosine B plus cosine A times negative sine B. And of course, if you write this the way we normally would, it's minus cosine A sine B. Okay, so nothing fancy involved there. There's only one time that I had to do the big work to find the formula for the sine of A plus B. And one time that you guys have to do the big work to find a formula for the cosine of A plus B. All the other formulas are very easy then to deduce. So if I go back now, that means we also did this one. Use homework and the opposite angle identities to get that one. And opposite identity angles will give you this one as well. Okay, so the formulas that I think you definitely should know for the CSET are the first two. The sum and formulas for the sine and the cosine. Okay, so the others you can relatively easily deduce if you would ever need them. Okay, so we've done all the sum and difference formulas. Then next formulas that show up quite often are what we call the double angle formulas. But let's first do I can't say a practical application, but let's do an application. Can we find an exact formula or expression for the sine of 15 degrees? And once we find it, you'll see why we don't make it. You guys memorize it. We can. Yes, Brent, but you guys are writing it. It's 45 degrees minus 30 degrees. So I'm trying to write 15 degrees either as a sum or a difference of known angles. Well, it is 45 degrees minus 30 degrees. Then we use our formula that says it's the sine of the first, cosine of the second, minus cosine of the first, sine of the second. The sine and the cosine of 45 degrees were what again? Root 2 over 2. And then, what is the cosine of 30 degrees? Root 3 over 2. And then the sine of 30 degrees will be a half. We can simplify a little bit, but it's not too bad. Root 2 times root 3, that's root 2 times 3 is 6. Root 2 times 1 is 1, so root 6 minus root 2 over 4. That is the sine of 15 degrees. So mathematically, it's cute that we can find it, but is it practical? Not really. Who wants to memorize that? But we can find it. Okay. Let's find the cosine of 75 degrees. Again, we want to write 75 as a sum or a difference of two known angles. This time it's the same two angles, but we're adding them. So the formula says it's the cosine of 45 degrees cosine second minus, there's a weird one there, the sum formulas for the cosine have a minus sign in them. Sine 45 degrees. Sine 30 degrees. We just did those, root 2 over 2. Cosine was root 3 over 2. And the sine is a half. So, although we got different way of getting there, it's exactly the same as the sine of 15 degrees. There is actually a general formula. In general, the sine of, or the cosine of 90 minus theta is the sine of theta. So 90 minus 15 degrees, that would indeed be the sine of 15 degrees. If I would ask you to prove this in general, what would now be the easiest way to do this? So if I ask you prove that the cosine of 90 degrees minus theta is always the sine of theta, you mostly want to use anything that we've already seen versus having to reprove it. So could you do something like the opposite angle formulas? Yes, but the easiest would now be the difference formulas. Easiest, use cosine of A minus B. Where your A is 90 degrees, your B is theta, you will almost immediately get the answer there. Okay, could you graph it? There's a relation between theta and 90 minus theta. Yes, but Once you have the difference and sum and difference formulas, this is much easier, right? So just nice little example to show there's ton of identities out there. Okay, the double angle formulas definitely have some applications. As the name of all these identities or formulas suggest, it deals about the double of an angle. So can we figure out the trig functions of twice an angle in terms of the angle? So here are the formulas. The sine of 2 theta is 2 sine theta cosine theta. The cosine of 2 theta, now there's all of a sudden 3. It's cosine squared theta minus sine squared theta, 2 cosine squared theta minus 1, or 1 minus 2 sine squared theta. You might wonder, why are there so many different ones? Well, because each one has a different application. I cannot show you guys the applications. You need to really take Calc 2 for that. But I can show you how to come up with these formulas. There's one for the tangent as well. 2 tangent theta over 1 minus tangent square theta. What would be the easiest way to come up with these formulas? Again, try to use what we all have. Use our sum formulas. Namely, what is the sine of 2 theta? That's the sine of theta plus theta. So we got that this is the sine of the first, cosine of the second, plus cosine of the first, sine of the second. That's really twice the same thing, so we get twice sine theta, cosine theta. So not a big deal. And now you basically do the same for the cosine and the tangent. If you do that for the tangent, you will get this formula. If you use it for the cosine, you will get this one here. So let's maybe have a look at this guy here, the cosine, where that comes from. So cosine of 2 theta is cosine of theta plus theta. So we get cosine of the first, cosine of the second, minus sine of the first, sine of the second. Oh yeah, that's cosine squared theta minus sine squared theta. So that shows this guy. So how can I now prove that this is the same as 2 cosine squared theta minus 1 and the same as 1 minus 2 sine squared theta? What's going on to go from here to here? Because once we figure that out, then we probably can figure out how it happened. A difference of squares will, Emma will, that we will factor. But so there is something here in the first formula that is not in the second one. What is gone? The sine squared is gone. And all of a sudden we have a 1 there. So have we seen anything that allows us to get rid of sine squared? Yes, we had cosine squared theta plus sine squared theta is 1. So what is the sine of square theta? It's 1 minus cosine squared theta. So when I substitute this in here, I get cosine squared theta minus 1 minus cosine squared theta. So we get cosine squared theta minus 1 plus cosine squared theta, 2 cosine squared theta minus 1. Again, you might wonder, what on earth is the point of this? Sometimes we want to get rid of cosine squared theta, and we have in a formula. And we've seen now two ways to do this. Namely, you could get rid of a cosine squared theta by writing it in terms of sine squared theta, or you could write cosine squared theta in terms of cosine 2 theta. So it all depends what you want. Would you rather have sine squared or cosine 2 theta in your answer? Well, that depends on your application. They both have their uses. Okay, so that shows you how to get this guy. How would you get 1 minus 2 sine squared theta? Well, you would just replace cosine squared theta by 1 minus sine squared theta. So I think for the double angle formulas, that these two are pretty useful for us. And that, I would say, is really the end of the formulas that you need to know. Anything else that I'm going to do tonight is just showing what is out there and how you can get there. But there's no need to memorize them. Okay? So let's first do an exercise. So could you find the sine of 2 theta and the cosine of 2 theta if you know the sine of theta? And if you know that theta lies in the second quadrant. Okay, so you could actually find one of these two without this extra information. Which one of these two could you find if I only tell you that sine theta is 3/4? Can you then figure out what the sine of 2 theta is? Let's see. Let's go back to our formulas. So what do I need to know if I want to find the sine of 2 theta? I need to know the sine of theta and the cosine of theta. Right? So if I would only tell you that the sine of theta is 3/4, you cannot answer that question. But you could tell me what the cosine of 2 theta is. Why? If you use this formula for the cosine of 2 theta, you don't need to know what the cosine of theta is. You only need the sine of 2 theta. Okay? So let me write down the formulas here. So to find sine 2 theta, we need to know sine theta and cosine theta. There's no way out. So to find cosine 2 theta, sine theta is good enough. So how could I find the cosine of theta if I know that the sine of theta is 3/4 and theta lies in the second quadrant? There's roughly two methods, and one we've already seen tonight. If I give you one trig value and some information about the angle, you can use a right triangle to find the cosine of theta. Right? So let me call that method 1 is the right triangle. The right triangle is not for the angle, but for the reference angle. The sine of theta is 3/4. So what is the sine of the reference angle then? Also 3/4. Okay, the sine is which two sides again? Opposite over hypotenuse. So what do you want to pick for your opposite side? What do you want to pick for the hypotenuse? You're going to make the opposite side 3 and the hypotenuse 4. Then you can figure out using Pythagoras the other leg. How much is the other leg? How much is the adjacent side? Square root of 4 squared minus 3 squared. So that's the square root of 7. Okay. So then, what is the cosine of theta plus or minus the cosine of the reference angle? What is the cosine of the reference angle based on this picture, on this right triangle? Adjacent over hypotenuse. Now I just need to know if we need the plus or the minus. No? We're in the second quadrant. In the second quadrant, is the cosine positive or negative? Negative. Okay, so my cosine is negative root 7/4. This is what I mostly do. I really like this method of the right triangle. But the second method is using a trig identity. I don't like this as much because that means you need to know more trig identities now. So we know the sine, we want to find the cosine. Which trig identity relates sine and cosine together? So I'm looking for an identity that involves a sine and a cosine. Correct. But I would say one of the basic identities. Let me scroll back to what those are. Sorry, I've got quite a bit here. Is these guys here. Now, this also shows how we can use them for the others. If the tangent is given or the secant is given, you would use the second and otherwise the third. So if you can use the first one, that's easy. But that question that we had once, like, let me see if I can go. The tangent is given and the sine is negative. Could you find the cosine? Yes. You could use the second identity to find the cosine. I find that more complicated. I prefer a right triangle. But it is not wrong to use those identities. So let me quickly get back there. So the second method was use the trig identity. So cosine squared theta plus sine squared theta is 1. I want to know what the cosine is, so I solve for the cosine. Can you solve this equation for cosine theta? That involves a couple of things. First, you have to move the sine squared to the right. Right? Then we have cosine squared theta. is 1 minus sine squared theta. And how do I get rid of the square? You take a square root. But here is the problem. This will lead, oh, sorry. I shouldn't have. Sorry, everything is falling apart here. So cosine squared theta is 1 minus sine squared theta. You take a square root. However, whenever you take a square root, it's plus or minus. And if you forget that, you would make a mistake here in this case. So let's plug in our values. Plus or minus 1 minus 3 over 4 squared. You do the calculations, you find exactly the same numbers. Plus or minus the square root of not 7 over 4, square root of 7. Everything over 4. So then you still have to figure out, just like we did in the other method, that it's the minus. Okay? So another reason why I don't like the trig identity method too much, it's too easy to forget that plus or minus. Either way, we now know that the cosine of theta is negative root 7 over 4. Can we now find sine 2 theta and cosine 2 theta? Yes. What is the sine of 2 theta? It's 2 cosine theta sine theta. So that's 2 times negative root 7 over 4 times 3/4. So that becomes, if we simplify, negative 3 root 7 over 8. What is the cosine of 2 theta? You could basically use any of the 3 formulas that we've seen. If you only know the basic one, then you would write it as cosine squared theta minus sine squared theta. But if you knew the one with just the sine in it, then we could have done as 1 minus 2 sine squared theta, and we never even had to find cosine theta. Here, let me use what we have. And we get 7 over 16 minus 9 over 16, which is negative 2 over 16, or negative 1 over 8. Okay for everybody, and my apologies again. Certain parts of the screen went out the moment I touched that eraser. But so that would be for us about the only application of these double angle formulas. Okay? So let's continue for the rest of the evening with some more identities. The half angle formulas, again, no need to memorize. But they are about, could you find the trig function of half an angle in terms of the angle? So here are the formulas. The sine of theta over 2 is plus or minus the square root of 1 minus cosine theta over 2. The cosine of theta over 2 is plus or minus the square root of 1 plus cosine theta over 2. You can't figure out in general if it's the plus or the minus. You need more information. But what is truly amazing about the formulas for the tangent, there you can figure it out. So yes, you could say it's plus or minus the square root of 1 minus cosine theta over 1 plus cosine theta, but it's equal to 1 minus cosine theta over sine theta, or sine theta over 1 plus cosine theta. So that is kind of amazing. If you know the cosine and the sine, you can figure out the tangent of theta over 2. No plus or minus. You know exactly where it is. Oof. Any suggestions on how we could get there? As usual, these two are the basic ones again, because then taking the quotient should give us the tangent. The half angle formulas are really just a silly rewriting of the double angle formulas. Yes, Deepa, you could write sine squared of theta over 2 plus cosine squared of theta over 2 is 1. But what would that give you? That would give you that the sine of theta over 2 is plus or minus the square root of 1 minus cosine squared of theta over 2. So that is not what this formula is saying. It's giving theta over 2 in terms of theta. It really is a silly rewriting of the double angle formula. Namely, let me write the double angle formula in terms not of theta, but x or beta or anything like that. So what is the cosine of 2x? It was, there were two possibilities, three actually. It's 1 minus 2 sine squared x, but it was also 2 cosine squared x minus 1. Okay? And so what I'm going to do now is let x be my theta over 2. Then what does this formula become? The cosine of something is 1 minus 2 sine squared of theta over 2. What is that something I have to write here? Theta. My 2x becomes theta. So it's really nothing different. It's the double angle formula, which gives the double of an angle in terms of the angle. Well, you could also read that as it gives the angle in terms of twice the angle and solve it for that. So now we need to solve for the sine of theta. The sine of theta over 2. So first I move 2 sine squared theta to the left. And the cosine of theta to the right. Then we divide by 2. And finally, we take the square root. But we take a square root, and we have plus or minus. So almost none of the formulas that we're going to see now require us to do any big new proofs. It's using what we already have. Okay, so if you would use that the cosine is of 2x is 2 cosine squared x minus 1, then you're going to find the formula for the cosine of x, the cosine of theta over 2. So that gives you these two formulas. How useful are they? Well, we'll do an exercise on it. How could you get the formula for the tangent of theta over 2 now? That's the sine over the cosine. And so the sine is plus or minus square root of 1 minus cosine theta over 2, and plus or minus the square root of 1 plus cosine theta over 2. Now, the plus or the minus do not cancel out. We're just saying, I don't know if it's plus or minus. It could be that the numerator is a plus and the denominator is a minus. They could both be minus. They could both be plus. We really don't know. So the answer is still plus or minus. We still don't know if it's positive or negative. But the square root divided by a square root, I can combine in one big square root, 1 minus cosine theta over 2 over 1 plus cosine theta over 2. And then we see that the 2's cancel out. And we end up with this. So that proves this guy, but how on earth do we get these guys? Let me work on one of them, but that is more a little bit of a trick. Maybe that's what they call it, trigonometry. But it's nice, but it's not so obvious why this works. So what is the tangent of theta over 2? Well, that would be the sine of theta over 2 over the cosine of theta over 2. And now, excuse me, how could I get the regular formulas in there? How could I get sine or cosine of the sine of theta in there? Well, we can use a double angle formula. So remember that the sine of 2x is 2 sine x cosine x. So if you put x equal to theta over 2, what does that tell you? The sine of theta is 2 sine theta over 2 cosine theta over 2. You might wonder, why on earth would you want to do this? It's one way to a relation between theta and theta over 2. Okay, so this suggests something. I have sine of theta over 2. And I would like to get sine theta instead. So what am I missing in my numerator so that I would just have sine theta there? So here's what I have. And here's what I would want to have if I want sine theta. So what am I missing? What is not here that is here? So I have sine theta over 2. I don't have the 2, and I don't have cosine theta over 2. So that suggests that I just multiply this by 2 cosine theta over 2. Of course, I cannot just multiply by 2 cosine theta over 2. To undo that, I'm also going to divide by 2 cosine theta over 2. So, what do I have now? I got 2 sine theta over 2 cosine theta over 2 over 2 cosine squared theta over 2. My numerator is okay. But what do I do with the denominator? I got a cosine squared in there. I don't want a cosine squared, and I don't want to replace it with sine squared. I want to get rid of the square, but use a cosine. So what do we have for our formulas? The cosine of 2x was 2 cosine squared x minus 1. So what do we get if we again put x is equal to theta over 2? The cosine of theta is 2 cosine squared theta over 2 minus 1. So 2 cosine squared theta minus over 2 is, just move the 1 to the other side, 1 plus cosine theta. You can write it as 1 minus sine squared, but then we have 1 minus sine squared of theta over 2. We're trying to get rid of the theta over 2, so finally we get that this is sine theta over 1 plus cosine theta. If it's a little bit too much, that's fine. Again, this is not that important, but so we didn't really come up with any new formulas. It's all about how do you want to interpret these formulas. If you look at this formula, you can read it from right to left that says the sine of twice an angle can be given in terms of sine and cosine of the angle, or maybe this guy here, the cosine squared of an angle has something to do with the cosine of twice the angle. And that's what we're using here. Okay, let's do one formula on this. Let's use the half or double angle formulas to find the sine of 15 degrees. We already did this one, but we used then the difference formulas. So how could I use these formulas to find the sine of 15 degrees? That's 30 over 2. So the sine of 15 degrees is the sine of 30 degrees over 2. And our formula says it's plus or minus the square root of 1 minus the cosine of the angle over 2. Now we know which one it should be. Is the sine of 15 degrees positive or negative? Positive. So I know it's the plus. Oh, 15 degrees is in the first quadrant. Okay, what is the cosine of 30 degrees? Root 3 over 2. So if we now do a little bit of simplification, so that put on a common denominator, we get 2 minus root 3 over 2 over 2 squared. So that becomes 2 minus root 3 over 4 squared, which is 2 minus root 3 squared over 2. Okay. I do want, sometimes you get these really weird results. Before, with the sum and difference formula, we got this. We had square root of 6 minus square root of 2 over 4. Oh, sorry. Let me quickly try to rewrite this again. Okay. That's what we had before. I have to tell you, this is absolutely not obvious that these two things are the same. The square root of 2 minus square root of 3 is the square root of 6 minus the square root of 2 over 2. So it's pretty neat that we come up with two different expressions for the same thing. That's pretty neat. Another exercise, could you find the cosine of theta over 2 if you know the sine of theta, it's 5 over 13, and it is given that pi over 2, that theta is between pi over 2 and pi, between 90 degrees and 180 degrees. We know our formulas for cosine of theta over 2. It's plus or minus 1 plus cosine theta over 2 squared. So there's two problems we have now. I need to figure out if it's going to be the plus or the minus. And we're going to have to find the cosine of theta. Let's maybe first deal with the plus or the minus. So I do know, if I think of it in degrees, that my theta is between 90 and 180 degrees. So what does that mean for theta over 2 then? It's between 45 degrees and 90 degrees. So if theta over 2 is between 45 degrees and 90 degrees, it's in the first quadrant. So will its cosine be positive or negative then? Its cosine is positive. Right? So that solves the first problem. It's the plus. My second problem is now I still got to find the cosine of theta. We could use a right triangle, or we can use a trig identity formula. I like that right triangle, but the right triangle is for the reference angle. Okay, the sine of theta is 513. So what is the sine of the reference angle? 5/13. So we are going to pick two sides in our triangle. Which two sides do we pick, and what do you want to make them? Which side do you want to make 5? That should be the opposite side, and the hypotenuse is 13. Then we can use Pythagoras to find out what the other side is. This is the square root of 13 squared minus 5 squared, which is indeed nicely 12. So the cosine of theta is plus or minus the cosine of the reference angle. The cosine of the reference angle is 12 over 13. So we have another problem with the plus or the minus. Theta is between 90 degrees and 180 degrees. So theta is in the second quadrant. In the second quadrant, we are negative, the cosine. Okay, so we're almost done. We get 1 minus 12 over 13 over 2 squared. And when we do all the calculations, 13 minus 12 is 1. We get 1 over 26 squared. So we get 1 over root 26. That's the cosine of theta over 2. So the last remark there that I gave is more, we got to think about this one a little bit. So all of a sudden I wrote there that theta is between 90 degrees and 180 degrees, which means that theta is in the second quadrant. Could I have just written instead, theta is in the second quadrant? So where did we use that specific information? So what if I would just say that theta is in the second quadrant? Well, then this would still be the same. Because we used here that it's in the second quadrant. If theta is in the second quadrant, is it always true that theta over 2 will be in the first quadrant? It seems that the answer is yes, but it is actually no. So let me mark that here. Suppose that, I need a new board. So suppose that theta is between 5 pi over 2, which is 450 degrees, and 540 degrees. Let's see if we can draw where theta is. I start at my initial side here. I'm going counterclockwise. So first I got to go around one full time. That's 360 degrees. Then I do another 90 degrees. I'm at 450 degrees. If I do another 90, I'm too far. So my theta is somewhere in the second quadrant. But what can you tell me about theta over 2? Well, theta over 2 is between 270 degrees and 225 degrees. So let's graph where theta is. Theta over 2 is. Initial side on the positive x-axis. I gotta go at least 225 degrees and at most 270. So we go 90, sorry, we go 90, 180, 225, and this would be too far. So where is theta over 2? It's in the second quadrant, third quadrant. So it is impossible to figure out. If I just would have told you guys that theta is in the second quadrant, you cannot figure out where theta over 2 is. Could be the first quadrant, could be the third quadrant. So could have a plus or a minus in there. So it was just a little bit of a trick question. Like, is that the same information? No, it is not. So I really needed to give you guys some very specific information. Okay, sum to product formulas. These are used in an advanced Calc 2 class. What is the idea behind it? We want to rewrite a sum of trig functions as a product of trig functions. Let me give you guys the formulas, but the tough part is on how on earth could somebody come up with that? So the sine of a plus the sine of b is 2 sine of a plus b over 2 times the cosine of a minus b over 2. And there's formulas for a sine minus a sine. There's formulas for a cosine plus a cosine and a cosine minus a cosine. And then there's also formulas for the sum of two tangents. But how on earth could anybody come up with this here? Once I give that to you, what is one valid approach? I'm going to use the sum and difference formulas to work out the sine of a plus b over 2, a minus b over 2, FOIL it all out, and simplify, and then I'm going to get sine a plus sine b. So that is a valid approach, but it will not teach you how anybody came up with it. So here is more the idea behind it. Okay, so I want to do something with sine A plus sine B. But there doesn't seem to be anything I can do because I cannot factor that. They don't have anything in common. So my only hope is there a way that I could maybe expand, work out sine A, work out sine B, and then somehow things simplify? What are the only formulas that we have to expand is A and B would be sums. So we try to write A and B as, let me put that between quotes, sums. For yeah, what if I can write A as x plus y? Then what would the sine of A be? Sine x plus y. That would be sine x cosine y plus cosine x sine y. And I want to do something similar for sine b. Right? Now, if I write the sine of b as the sum of two completely different things, let's say v plus w, what am I going to get? Sine v cosine w plus cosine v sine w. If I add this, nothing is going to happen. So I want to have something here so that maybe something cancels out or so, or simplifies, or that I can factor out. So what do I basically want? If you check these, how could I have anything cancel out? Well, basically my x needs to be my v and my y my w. So I need something like b is, well, x plus y doesn't make any sense either because then I get the same thing. I want to try x minus y. If I get the sine of x minus y, then I get sine x cosine y minus cosine x sine y. And when I add them, what do I get? 2 sine x cosine y. Sine A plus sine B. If I can write my A as x plus y and my B as an x minus y, I don't even know if that's possible. But if I can, then I can rewrite sine A plus sine B as 2 sine X cosine Y. So now the only question is now, is it possible? Well, can I find an X and a Y such that A is X plus Y and B is X minus Y? Solve this system of equations for X and Y. So X plus Y is A, X minus Y is B. How can we easily solve this for X? These are linear equations. What's the easiest way? We just add them. What do you get if you add those two equations? We get 2x is a plus b. So my x is a plus b over 2. And what does y need to be? Or how can we get rid of x and get my y there? If you subtract them, you get a minus b is 2y. So x has to be a plus b over 2. Y is a minus b over 2. Let me recap a little bit what we did here because it might really seem like a hat trick. But if I want to simplify sine A plus sine B, I got to make it more complicated because there's nothing I can do about sine A, sine B. So could I write A as a sum? Because then I can expand it. Same with B. In order for me to add them and have anything going on, it seems like I need to write B as x minus y and B as x plus y. Then I figure out what my x and my y should be. So what do we have? The sine of A plus the sine of B is 2 sine of A plus B over 2 times the cosine of A minus B over 2. But the way we came up with it was not by, I believe you, and I'm just going to work it out and check that it works. We actually came up with it. We tried to factor sine A and expand A and B. And then the formula was right there. Okay, so if I go back here, that does this guy. Very similar. If instead of adding you subtract, you're going to get this guy, or you use the opposite angle formulas. And you can try the same for cosine A plus cosine B and cosine A minus cosine B. In the last couple minutes I have, I want to talk about tangent A plus tangent B. That one does not come from expanding A and B. So, sorry, let me show you where the tangent of A plus B then comes from. Tangent A plus tangent B is, well, the tangent is sine over cosine. I can put this on common denominator. The common denominator is cosine A cosine B. What is what does my numerator become? I need to multiply my sine A by so putting them on common denominator, the sine A gets multiplied by cosine B, and the sine of B gets multiplied by cosine A. And that is a formula which is the sum for the sine of A plus B. So there is a way to rewrite the sum of two tangents as a product, it's sine of A plus B over cosine A cosine B. So this one has nothing to do with trying to expand, but we did change a sum into a difference. Okay, that's it for tonight. Again, make sure to understand that the important formulas were the sum and difference formula for sine and cosine, not the sum to product formulas, not the half angle formulas. That was just to show you what we can do. So we will continue next week. I got very little bit to go. So tomorrow I'll email you guys some exercises and the material for next week. And then before that, I will give you guys the solutions to these exercises as well. Okay, so tomorrow you guys can check out the recording if you want. It should be ready by then. So if anybody has a question, you can just type it in the chat box. Okay, otherwise, have a good night, and I will see you guys next week on Wednesday. The recording, it is the same link as the link you used to attend today. So if tomorrow you click on that link, it will take you to the recording.